So welcome back to image processing lectures. Today we are going to start with image compression. Now why we need compression and what are different ways of applying compression techniques that we'll see in this unit. So you must be using compression algorithms or applications like WinZip, WinRAR. Why we are doing this? To reduce the size of the data so that the storage requirement will be less, or if you want to transmit the data from one place to another place, okay, the bandwidth required will be very high if the size of the data or size of the image is very high. So if you compress the image, the bandwidth requirement will be less and storage requirement will be also less. So there are two types of compression techniques, lossy and lossless. We will see both in detail. So reducing the amount of data required to represent a digital image, okay, we are trying to reduce the amount of data which is required to represent that particular image. So what we are going to do is we are going to remove the redundant data. So generally compression is applied before the transmission, okay. First you will compress the image or a data and then transmit it, and when you receive you have to decompress, means you have to reconstruct the original image. So there are two broad categories: information preserving, that is lossless. What is the meaning of lossless technique? When you compress the image and decompress it back, there is no loss of information. Okay, so this method allows an image to be compressed and decompressed without any losing of any loss of information. So generally this is used for legal or medical records where you cannot afford to lose the information. Okay, like for example, if you have MRI or CT scan reports, and if you apply lossy technique, what will happen? The data information will be uh, lost, or data conveyed, information conveyed is not proper, then the diagnosis will be wrong, right? So we cannot use lossy technique for medical records. Then in lossy what happens? It provides a higher amount of data reduction but result in a less than perfect reproduction of the original image. So generally used for broadcasting, television images, video conferencing, facsimiles. Facsimiles means fax, okay, in which error is acceptable till a particular level. So we can reduce the size of the image in lossy technique till it is till the user is okay with it. Means if you compress the image, okay, and if you are not able to identify, recognize what is there in the image, then what is the use of that image? So you have to decide the predefined level till what you will be able to accept the loss of the information in lossy technique. So there are different applications of image compression. Tele-video conferencing, it can be used in satellite imagery for weather, documents and medical imaging, fax, and the control of remotely piloted vehicles in military and space. So we'll just go through the fundamentals. What is information? It is the message that is conveyed, and data, it is the word used to convey it. So data compression, the process of reducing the amount of data required to represent a given quantity of information. So what is data redundancy? The data that either provide no relevant information or simply restate that which is already known. Okay, so for example, a person, if you go for a movie and your friend goes for a movie, and you are narrating that in story to some third person, okay, so you may take 100 words to express or narrate the story, but the second, your friend may take 500 words. So the information conveyed, the story of the picture or movie is same, but you took 100 words and your friend has taken 500 words. So there is a redundancy. Okay, so that redundancy you can eliminate to compress. Okay, so let n1 and n2 denotes the number of information carrying units in two data sets that represent the same information. So n1 is the number of information carrying units by you, and n2 may be by your friend. So then the redundancy is given by RD equal to 1 minus 1 upon CR, where CR is a compression ratio. Okay, and compression ratio is given by N1 upon N2. So there are three cases. If n1 is equal to n2, what will happen? The compression ratio will be equal to 1, right? And Rd is equal to 0. Okay. So this indicates that the first representation of the information contains no redundant data. What is the first representation? N1. It doesn't have any redundant data. What will happen if n2 is very less than n1? So CR will be what? CR is n1 upon n2, right? So n1 upon n2, and n2 is very less than n1. So CR will tends to infinity and Rd will tends to 1. So this indicates that significant compression is this implies the significant compression and highly redundant data. In other case, if n2 is greater than 1, then compression ratio will tends to 0, right? Because n1 upon n2, and n2 is very high than n1. Then Rd will tend to minus infinity. This indicates that the second data set contains much more data than the original representation. So this is undesirable case of data expansion. CR and Rd, that is compression ratio and redundancy, lie in the open interval from 0 to infinity and minus infinity to 0 respectively. So there are three basic data redundancies: coding redundancy, interpixel redundancy, and psychovisual redundancy. So coding redundancy is reduction with respect to data representation. These all three redundancies we are going to see in detail, and we will solve problems also based on this. Okay. So coding redundancy is reduction with respect to data representation. How you are going to represent the image, whether how many bits you are going to use to represent the image. Okay. Interpixel redundancy is reduction with respect to the image representation. And psychovisual redundancy is reduction with respect to the image content. So image content means maybe contrast, colors, brightness. These are the image contents which we are going to alter or compromise. So these three things we are going to see in detail. So data compression is achieved when all three of these redundancies are eliminated, or any one or any two redundancies are eliminated. So coding redundancy. In coding redundancy, we are going to talk about code, code word, and length. So what is code? It's a system of symbols, okay, used to represent a body of information. So instead of writing 7, I'm going to write 111. So 111 is a code for 7, right? Code word. Each piece of information is assigned a sequence of code symbols. This is what I told. Suppose code is 7, then you may use the information, that is 111 sequence or some other code to represent that particular symbol. The length, the number of symbols in each code word, maybe 3 bits, 7 bits, 5 bits. Okay, so this is the length of that code. The discrete random variable Rk, what is Rk? Rk is a particular gray level value. In the interval 0 to 1 represents the gray level of an image, and that each Rk occurs with the probability PR of Rk. So this is what we have seen in histogram also. So probability of the particular gray level, okay, is given by the number of time that particular gray level occurs divided by total number of gray level. Okay, so k varies from 0 to l minus 1. So what is L? L, you know, number of gray levels. Nk is the number of times that the kth gray level appears in the image, and n is total number of pixels in the image. Okay, so if I want to find out a probability of gray level equal to 7, so what I am going to do, I am going to calculate how many times the 7 is occurring in the image, and I am going to divide that number with the total number of pixels in the image. So average number of bits required to represent each pixel is given by this formula. L average equal to summation of length of that particular gray level, okay, number of bits used to represent that particular gray level. Suppose I want to find out how many bits are required to represent gray level 7. So ideally for 7 binary number you require 3 times 1, right? 1 1 1. So length of that particular gray level value, okay, and the probability of that gray level value. So if you multiply it and add all the with respect to all the gray level values, you will get L average. We will solve one problem based on this later on, then your ideas will be more clear. So this is just an example. This is in coding redundancy, this is also known as variable length coding. Okay, why it is known as variable length coding? Suppose I am telling you that there is an image matrix having 3-bit image. Okay, what is the meaning of that? Suppose there is a 4x4 image matrix. So each gray level value we are going to represent using 3 bits, right, uniformly. So 4x4 image means there are 16 pixels and we are going to represent each pixel with 3 bits. So that is called as fixed length coding, because each and every gray level is represented by fixed number of bits, right? Here I am talking about variable length coding. So here we are not going to use fixed number of bits for all the gray level values, but depending upon some predefined criteria, we are going to change the length of each value, length of code length of each gray level value. So this is known as Huffman coding actually. Okay, this you must have learned in communication. So what we are going to do here is we are going to sort all the values depending upon their probability from highest to lowest, and then we are going to assign the codes to each one. So here the important thing you have to remember is the value which is repeating more number of times means the occurrence is more number of time, then you are going to assign less number of bits. Okay, and the value which is having less number of times, the value which is occurring less number of times, you are going to assign more number of bits to that particular value. Okay, so here you can see here you can see there are values from 0 to 1, actually 0 to 7, but we have normalized it by dividing that with each value by 7, that is 7 is the maximum value for 3-bit image, and these are the probabilities given. Okay, so they have sorted it from highest to lowest, 0.19 to 0.02, right? Now this is code 1. Code 1 is what? Code 1 shows that it's a fixed length coding. So if the image is 7-bit, the 3 bits are required to represent each value, right? 0 to 7. So this is a fixed length coding. Now how many, that's what is written here. See, the length is L equal to 3. Okay. Now what I said before is by applying some algorithm, we are assigning less number of bits to the highest probable value and more number of bits to lowest probable value, right? How to do that? That will solve the problem later on. Okay, that we'll see later on. Okay, so here now you see the length. Now previously it was 3, now it is through 2. Similarly here 3, then 2. Okay, here it was 3, now it is 6. So this is variable length coding. Now if you want to calculate the L average, what you will do, you will first take the length of the code, that is 2, okay, and what is the value of the what is the probability? 0.19. So 2 into 0.19 plus 2 into 0.25 plus 2 into 0.21, so on till the last, that is what, 6 into 0.002. What I am getting is 2.7 bits per symbol. Okay, I have here it is 2.7 bits per symbol. So what was the length before? 3. Now it is 2.7 bits per symbol. So compression ratio will be n1 upon n2, that is 3 upon 2.7, that becomes 1.11. Okay, so what is RD? RD is equal to 1 minus 1 upon redundancy, 1 upon 1.11, that becomes 0.099. So that is 10%. Okay, 10% data redundancy. So this is the example for coding redundancy. We'll solve the problem based on this later on. So coding redundancy, gray levels of an image uses more code symbols than absolutely necessary to represent each gray level. Redundancy is present when gray levels are represented with natural binary code. So natural binary code means whenever I say, if I say it's a 5-bit image, how many bits required? 5 bits throughout for all the gray level values. So that is called natural binary code. Okay, so assigns the same number of bits to the most and least significant probable values. Now interpixel redundancy. Images usually have regions of constant or similar values. Suppose I am taking a binary image. So binary image, you will either have 0 or 1, that is black or white value. So this is called as interpixel redundancy. So this technique is known as run length encoding, RLE. Suppose I have an image, okay, black and white image, and in a row, okay, in a row you have 5 black pixels, then maybe after that you have 10 white pixels. So how I am going to write that? 5 times I will write 1 and then 10 times I will write 0, right? So 5 white pixels and 10 black pixels I said. So instead of writing this way, can I write as a count and value pair? Okay, so here I have mentioned here one example. Okay, the sequence is 1 1 1 1 1, so it is 6 times 1 and then 10 times 0 and then again 5 times 1. So instead of writing this entire row like this, if I can write in the bracket 6 comma 10, that is 6 times, this is C here, 6 times 1, so I can write 6 and 1, then I can write 10 and 0, then I can write 5 and 1. So this is called as count value pair. So instead of using individual codes for black and white pixels in a binary image, we can encode runs of black and white pixels. Okay, so there is a fixed size for the count value, that is 1 byte. Okay, so RLE is used for binary images and commonly used for fax transmission. Can also be used for gray level images. So this type of technique will not work, or it is not efficient, effective in terms of noisy images. Why? Because in noisy images you may get a fluctuation 0 1 0 1 0 1. Okay, so 0 1 0 1, for each value you have to write like this. Suppose 1 is occurring 1 times, then followed by 1 is occurring count and value. Okay? 1 is occurring 1 time, then 0 is occurring 1 time, then again 1 is occurring 1 time, then again 0 is occurring 1 time. So this becomes a negative compression. So it's better not to use this interpixel redundancy for noisy images. Okay. Third redundancy technique is psychovisual redundancy. This particular redundancy technique, okay, if you want to eliminate, you are going to take into consideration the inputs from the subject, that is the user. Okay, so certain information simply has less relative importance than other information in normal visual processing. So this information is said to be psychovisually redundant. So for example, contrast, colors or brightness. Okay, so this all the things are subjective, so you can reduce these values and you can achieve the compression. So psychovisual redundancy reduction deals with lossy compression technique, so in contrast to coding and interpixel redundancy reduction. So you should always remember, if you want to develop a system which is lossless, you cannot include this psychovisual. Okay, you have to take care, or you can include coding and interpixel redundancy removal techniques if you want to develop a lossless technique. If it is a lossy technique, then you can include psychovisual redundancy elimination in that. So usually remove visually irrelevant information like small details in space or colors from images, and color reduction, for example color reduction or resolution reduction. So resolution reduction, suppose a picture is given as 1024 by 768 and can be reduced to a picture of 512 by 384. So by merging 4 pixels to 1, so we are applying averaging in this. The content will still be recognizable and the compression ratio is 4. Another example is color reduction for 24-bit image, that is 3 bands and 8 bit for each band. Okay, representation of each pixel is able to represent 2 raised to 24 colors. Reducing number of colors to 256, that is 8 bit, using 8 bit yields to a compression ratio of 3. Obviously you are going to lose something, but if the subject is okay with this, you can go ahead and use it. Now how to measure the loss of psychovisual? So that is known as fidelity criteria. Removal of psychovisually redundant data results in a loss of real visual information. So fidelity criteria is the possibility to measure the loss of information. There are two types: objective fidelity criteria and subjective fidelity criteria. In objective, we are going to use some mathematical formula. In subjective, we are going to take the opinion of the subjects, that is users. So what is objective fidelity criteria? When the level of information loss can be expressed as a function of original image, the compressed and corresponding decompressed output image, okay, that is called as objective fidelity criteria. So root mean square error between input and output image is given by Exy equal to f bar xy minus f of xy, where f of xy is the original image, f bar xy is a decompressed image. Okay, so the formula is given here and we can compute the ERMS. It is very simple technique, simple and convenient for calculating the information. Next is subjective fidelity criteria. It is accomplished by showing a typical decompressed image to many people at the same time, or many viewers at the same time, and then we take the average of their opinions or evaluations. The evaluations made by means of side-by-side comparisons of original image and compressed or decompressed image. Means what they are doing, suppose you are sitting and they will show you three images simultaneously, maybe on three displays. First is original image, second is compressed image, and third is decompressed image. Okay, and then they will take the opinion. Frankly speaking, or practically speaking, compressed image you won't be able to recognize as image, right? But you have to compare the original image and decompressed image, and if you are happy with it, we can go ahead with the compression techniques. Now we'll see a general compression system model. Okay, so all the three techniques, all the three redundancy techniques uh, for compressing the image are combined to form a practical image compression system. So here f of xy is the original image, which is given to source encoder, then it is given to channel encoder, then there is a channel, it is transmitted through a channel, received, and then it is decoded using channel decoder, and then it is given to source decoder, and you get f cap. So if it is a lossless technique, the f cap will be equal to f. If it is a lossy technique, then f cap may not be equal to f. Okay, so f cap is a reconstructed image. Okay, so this is what is written here. If f cap is equal to f, then it's a lossless technique. If f cap is not equal to f, then it is lossy technique. So both encoders and decoders are independent functions of subblocks. Encoder is made up of source encoder and channel encoder, and source encoder is used to remove the input redundancies. The redundancies which we have learned just now, okay, we can eliminate in source encoder, like psychovisual, then coding and interpixel redundancies we can remove in the first block, that is source encoder block. Then there is a channel encoder which increases the noise immunity. If the channel is not noisy, you can eliminate this. Okay, then after receiver, in the receiver, the first block is decoder, which is made up of channel decoder followed by source decoder. So if that's what here I have mentioned, that if the channel between encoder decoder is noise free, then no need to use the channel encoder and decoder. So what is this source encoder? I said it can eliminate all the three or any one or any two redundancies. So there are three stages in source encoder: mapper, quantizer and symbol encoder. So mapper takes care of run length coding. So transforms input data into a non-visual format to reduce interpixel redundancy in the image. So what is non-visual format? Obviously when I going to change, when I going to represent the data in some other format, the picture won't be in the picture form. You won't be able to see it. For example, when you apply a when you zip a file, can you see that file, contents of the file? Unless otherwise you are applying unzip. Okay, so when you compress it, it may not be in the picture format, when it will not be in picture format. Okay, you have to decompress it to see it in the picture format. So mapper is for used for run length coding. Quantizer, this stage reduces the psychovisual redundancies of the input image. So it is irreversible operation. Why? Because I said it's a psychovisual, so it's a lossy technique. Whatever you have lost is lost permanently. So it is an irreversible operation and must be avoided in error-free compression techniques. Okay. Third is symbol encoder, which assigns the shortest code word to the most frequently occurring gray level value and thus reduces coding redundancies. So this is used for Huffman coding. Suppose I am going to, this is what I told you, right? You are going to count the frequency of occurrence of a particular gray level value. For more probable value, you are going to assign lowest number of codes, and for less probable values, you are going to assign more number of codes. So the topmost image is A, that is above image, that is source encoder and source decoder. In source encoder you have mapper, quantizer and symbol encoder. In source decoder you have symbol decoder and inverse mapper. You cannot have inverse quantizer, because why? Because I told it's a used for lossy technique, psychovisual, and it is irreversible. So you cannot have inverse quantizer over there.